All right, welcome people on the internet. I'm going to share my desktop, and we're going to play with a little bit of fractions. So this was from a little bit from section 1, it's a little bit from section 2. So the goal was to find 5 fractions between 1/9 and 1/8, and there's lots of different strategies one might employ, and so that's why I put you in the groups to give it a shot. So a lot of people, when they first look at it, were stuck in the whole modeling fractions, part of a whole, add and subtraction. And so first shot, we might draw something like 1/9. And I saw various pictures of 1/9, drawing 9 lines across here, or 8, sorry. 1, 2, 3, 4, 5, 6, 7, 8. So that's a 9th would be one of these suckers here, and 1/8. Roughly the same size hole. Even numbers are easier because I can just keep cutting things in half to some extent. And there's 1/8. And it's hard to tell in this picture which is the bigger, but if you think about eating pizza, which always inspires me to do math, if I had a choice between a 1/9 of a pizza and an 1/8 of a pizza, well, if it's an 1/8 of a pizza, it's the same stuff, but they made less portions. That means I get more. Right? So I would prefer this one. So 1/8 is bigger. Agreed?
Yes.
But this picture is not really helping me find something in between. Although I could employ the cut each cake like the other strategy from the other day to make them comparable, because right now they're slightly different size slices. So then I could cut this guy in 8s, there's quarters, and here's 8s, and I could cut this one in 9ths. And so now what size pieces do I have up here? 8 by 9 is 70, I have 70 seconds, right? So how many 70 seconds is the 1/9? Well, I took that 9 and I cut it into 8 pieces, so it must be 8 70 seconds. And this guy right here, I cut it in 9, so that one piece must now be 9 70 seconds. And so now I can clearly see that the 1/8 is bigger, because now they have the same denominator. Another trick to comparing two fractions is to use that cross-multiply kind of algorithm I talked about before. If we were to cross-multiply here, 8 times 1 is 8, 9 times 1 is 9, 8 times 9 is 72. So that cross-multiplying algorithm allows me to quickly compare two fractions and see which one's bigger, or if they're equal. So that was that arrow algorithm for addition. I'm not going to bother adding the numerators here, but now I can use that to see, hey, 1/8 is bigger. All right. However, couldn't I use the arrow algorithm for subtraction or addition? We talked about that last time.
No.
All I do is add or subtract. Okay. So I have a couple options here. If I were to subtract these two, now right now they're kind of in backwards order. If I were to take 1/8 minus 1/9, my crisscross multiply thing tells me that this is a 9. Come on, there you go. That's an 8. And this is a 72. And so the answer must be 9 minus 8, or 1 out of 72. What does the subtraction tell me physically about these two numbers? Like if I were going to consider the number on it. They're 1/72 apart. Yeah, that's the distance they are apart, is what that tells me there. Okay. So if I know how far apart they are, the distance to get from here to here, can I use that to maybe identify the midpoint?
Yeah.
Yeah. So to get to the midpoint, I go half that distance, which would be how far?
144.
Yeah, from there to there would be 1 out of 144. And so I could add that 1/44 to say the 8 70 seconds. That would give me the number in the middle. Okay, so it's new page, let's employ this algorithm. So I have 8 70 seconds. I want to add 1 out of 144. Now here's a choice where I'm going to choose not to use the arrow method, because I can kind of see a lowest common denominator. Can anyone else see the lowest common denominator? What is it?
72.
144, excellent, Hillary. You guys see out of the corner of your eye watching my facial expression. Yeah, so yeah, we doubled 72 to get 144, so now I can just double top and bottom here. Adding those together gives me 16 plus 1, or 17 out of 144. That must be the midpoint. Now it turns out I already had that answer hiding on the other page. Let's go back a page.
Oh, 9 plus 8.
Yeah, 9 plus 8 is?
17.
Bob, you need that. Okay, yeah, if I add them and then divide by 2, isn't adding numbers divided by 2 give me the middle?
Yes.
Boom, there's the middle. Right? So thinking about this number line wise, let's go back here. Blowing it up, if I zoom in, here's 1/9 and here's 1/8, and dead smack in the middle there is 17 out of 144. If we wanted to, we could add these guys up and divide by 2, and that would give me the number right there. I could add these 2 up and divide by 2, that would give me the number there. Couldn't I repeat that?
Subtract that one?
Well, I'm just showing slightly different ways to think about it. So I'm offering a whole bunch of different strategies. Subtracting gives me the distance from here to here. Adding and dividing by 2 puts me right in the middle. Okay. Get the difference there? So I could just keep finding any 2 fractions, add them up, divide by 2, I now know the one in the middle. Add them up, divide by 2, I now know the one in the middle. Add them up, divide by 2, I now know the one in the middle. It's a fair amount of work, but not too much. Especially if I have a calculator. All right, so I saw you guys whip out some other techniques to do this. So that's one, playing around with the middle. Let's see, I saw a few people write down the decimal versions of them. And so let's see, 1/9. If we take 9 into 1, we get 0.1111, and that just goes on forever. Sometimes we write that as 0.1 where the 1 repeats. 1/8, 0.125. I'm pretty used to that one because I use a tape measure a lot, and tape measures have halves and quarters and eighths and 16ths and some up to 8 seconds. And so I know most of those decimals. Well, let's see, we talked about this a little last week. When I look at that and I say 0.125, that's slang. Does anybody know the correct way to read that?
0.125?
Not still slang. What's the proper way to read that number? 125 thousandths is the proper way to read it. Yeah, the proper way to read a decimal is to identify the furthest place value, tenths, hundredths, thousandths. So this would be 125 out of 1,000. This number right here, it's just a little bit bigger than 111 out of 1,000, isn't it? So based on that, could you name some fractions in between there?
Yeah.
Give me one.
112.
112 1,000ths better be in the middle there, shouldn't it?
113.
130, 124 out of 1,000. So I could just name those suckers all day long. Well, that's not true. I could have quite a few of them. I get 13 of them in there. That's pretty cute. Okay, so a few people employed that strategy, and then they reduced them, which I thought was pleasant. Thank you for reducing those. So do you see another cute way to do it? No?
Yes, please.
Thank you. All
Oh,
right.
did you say somebody?
Yeah, somebody said yes.
I thought you said, is there someone that has another?
No. Oh, let's see. Oh yeah, Christian, you guys, and Adrian, you have a cute way. Now let's look at your cute way before I do mine. So let me see. Help me out.
Here's the
Here's your map to it.
So for every, I basically did 1/8.18.
Oh, right. Okay. So here's 1/8 right there. No, 1/9. That's 1/9 right there. And this is 1/8 over there. Now, if the denominator gets bigger, but we leave the numerator alone, things get smaller, right? So if I made this denominator a little bigger, like 1 over 8.1, that's got to be slightly smaller, right? Because it's got a bigger denominator. It's a fraction. It's not a traditional fraction. That's called a complex fraction. It's a fraction within a fraction. Because I could say that's 1 over 8 and 1/10, right? 8 and 1/10, well, that's really, 8 times 10 is 80. That's really 81/10. So this is really 1 over 81/10. And 1 over means it got flipped. So that's really the same as 10 over 81. Which you could also see if you multiply top and bottom here by 10. Right, 10 over 81. Did you imagine there's all this really cute, wild math inside fractions? Who knew?
Never thought I'd say cute and math in the same sentence.
But you're getting it, aren't you?
I'm getting it.
All right. Okay, so then we just keep this up, 1 over 8.2 and 1 over 8.3, and we can get a whole bunch of them in there. What if I want more? Well, I could call it 8.11. That'll be a little less too, and you could just all day long do this, and then just multiply by a power of 10, top and bottom, and bingo, bango. Nice job.
There's an interesting pattern.
Okay. So, and that math is all about patterns, really. And it's fun when we can find games like this to play with our students and each other to kind of explore and get more comfortable. Are we feeling a little more comfortable after this? Compared to when you started it? Who felt totally lost and insecure at first? Yeah, that sucks, but it's good when you get past it, right? All right, so here's another trick that's kind of cute. Here is 1/9 on a number line, somewhere around there. Zooming in, 1/8 is somewhere over here. We found a common denominator before. Okay. And that's all right. What about if I did something, let's see. Yeah. So let's see, this was 8 over 72. And this was what?
9 over 72.
9 over 72. What if I call this 80 over 720 and 90 over 720?
You could go to 10 between it.
Then I get 81 over 720, so that's similar to what you were doing over there, right, Christian?
I said it's the same fraction as in what's above, so it added zeros, but it doesn't change the fraction that it is.
And I can just keep moving along that way and making it one. So somebody give me a fraction that's in between. 81 over 72. Now suppose I asked you to find me a fraction between those two, 720. You just throw another 0 on there. Yeah, you could say this is 800 over 720, 7200, and this one would be 810 over 7200, and now give me a number in between.
801. I mean,
801, 805. I mean, there's a whole bunch you can pick from. Let's go with 803 just for fun. 7,200. So we found a few numbers that live between 1/9 and 1/8. Question: how many are there? A bazillion. All of them. You say Brazilian? Is that like a person that lives in Brazil, or is it a really big number? Yeah, there's a lot of fractions in there. Could we list them all?
Probably not.
We could. So what do we call that mathematical idea? Yeah, there's infinitely many in there. And this is one of the crazy things about fractions.
So is there infinitely between every fraction?
Yeah, it turns out between any two fractions you pick, there's infinitely many other fractions in there. So there's infinitely many fractions between 0 and 1. Well, right around here is 1/9, and right next to it, closer than that actually, is 1/8. And there's infinitely many fractions that live in there. And you pick the closest two you found and zoom in, there's infinitely many that live in there too. Infinity is a wacky idea. We can't count them all. We could put them in order. There is a way to do that, but we can't count them all. And want to hear something even crazier? Oh, no, we'll wait till next week. That's enough crazy stuff. Kelly?
For some reason I was thinking of imaginary numbers.
Oh, imaginary numbers. Yes, they live in a slightly different place. So one way to think about imaginary numbers, the I square root of -1 idea you've probably seen in classes. If you take two magnets and you put them together, some orientations, they suck to each other, right? But other orientations, they repel each other. Do they ever touch?
They repel, they should.
Right, it's really hard to make two strong magnets touch each other if they're opposite, right? Can you see what's making them not touch? It's like there's an invisible force in there, like Star Wars kind of force, repelling them. That's I at work. You can't see it, you can't exactly feel it, but it is there doing stuff. It lives in our reality.
Isn't I, what was it? It was like the 0.5 of a negative. Something like that. It takes 2 I's to make a negative and 4 I's to make a positive.
Oh, that's a whole nother thing. Well get to that later in the next
That's
chapter.
not fractions.
Yeah, we'll get to that in the next chapter. Okay, so that's enough here, I think. Someone say about this? No. All right, we're going to move on. So, oh no, there's one more thing. So let's go back to the 1/8 plus 1/9 for a second. Hello.
Hello.
All right, we were just reviewing. Did you just get here, or have you been there a while?
I just got here.
Okay. We were reviewing some stuff from 6.1 and 6.2 with the game. Back. There it is. Find 5 fractions between 1/9 and 1/8. And we employed, after struggling greatly, a bunch of different strategies. And so the notes for that I'll post in DocShare.
Okay.
So we'll take a look at it later. And we were just about to review one more idea from 8.2 and then move on, no, 6.2 and then move on to 6.3. All right, so I mentioned the arrow algorithm, and Kelly found some books online that oh, you found it in the classroom, okay. Teacher was using it in the classroom. And instead of calling it the arrow method, they called it the butterfly method. Because what they did was, I think I'm drawing this right, did they circle the bottom? They put 2 little arrows or something? Not positive, okay, I'm gonna circle. So they said, let's multiply those 2 numbers, that gives us 72. 2. And then we grab those 2 right there, 1 times 9 is 9. And then 1 times 8 is 8. Equal butterfly. Isn't that? That is the butterfly method. I'm going to show my daughters that tonight, and they're going to be so excited.
They're gonna do way better than that.
They're going to do way better than that. So this is the butterfly method.
We already got it.
So that shows me right there, the answer must be 17 out of 72. Okay. Next. So just as a quick review, we're still playing with fraction models and algorithms. I'm going to go back to models for a minute. We had 5 different ways to model what a fraction was, and we can use some of those models to explain how we get an answer from addition, subtraction, multiplication, or division. We're going to move on to multiplication and division next, but first we need to review some of our models. Help me out. What were our models for what a fraction means? Number line was 1, yep.
Part of a number.
What is a fraction? Part of a whole.
Part of a group.
Whole, yep. Part of a group.
Division, ratio.
Division and ratio, yep. Part of a group. Or division. And 5 a ratio. So those are the different physical models where fractions turn up in our reality. And we can write stories and draw pictures to show all of those. So we're going to pick one of those, and we're going to go try and explain what multiplication is next. So, thinking back to last term, multiplication, what were our models for multiplication of whole numbers?
Models.
Yes, models, not algorithms, models.
Array.
Array model. Yeah, that's
Area.
one. Area was another. Array. Area. Oops. Area. Just erase. What else? Think.
Repeated addition.
Repeated addition, nice. Repeated addition. And although the area one is my favorite, there is one we haven't listed yet that actually is the most popular. Groups of, yes. And there was a fifth one we did. I don't really care about that one. I don't like it as much. And so we're going to pick one of these, and we're going to try and show what multiplication means. So I think I'm going to start with the groups of. So just thinking back, 3 times 5, 2, let's say, literally means 3 groups of 2. And so I can draw that. Here's one group of 2, here's another group of 2, and here's another group of 2. And that's a slightly different picture than I would draw for 2 groups of 3. The orientation would be different. So I'll see if I can extend this to fractions. So suppose I tried something like 2 groups of 1/3. Do you think we can illustrate that? Can we draw a third? Yeah, we could use a cake. So here's a cake. Here's some thirds. Here's one group of a third. Here's another cake. Here's some thirds. And here's another one. So right there is 2 groups of 1/3. Now, it's kind of like addition, really. I have to combine and count them. So how many groups of 1/3 do I have? 2, and if I put them together into a single cake, can I give them a different name? Oh shit, wow, look at that. And we could call it 2/3. So I put this guy here and this guy here, and now I can say that this is 2/3. That worked. Now, as we know from whole numbers, it's a different picture if I switch the order. So I'm going to try and switch the order, see if I can make sense of it. Can I make 1/3 groups of 2? Ooh, that's interesting. 1/3 groups of 2. A third of a group. Oh, I can make a third of a group, couldn't I? Just like I can make a third of a whole? All right, so let me see, let's try that. So 2 is a whole number, right? Well, here's one whole, and here's a second whole. And then fraction 1/3, I guess I could do something like slice, slice. And I want to take 1/3 of that group of 2. So maybe I'll just, shade one of those bars. Like I could shade across here. That seemed like an adequate interpretation. 1/3 of a group of 2. What do I call that in the end? When I regroup and put that together. Yeah, if I draw a single hole and redeposit this guy and this guy, then yeah, I still get 2/3. Slightly different way of getting there. Still 2/3. That's kind of cool. That worked. Kristen, you had a comment, or were you going to tell me to do that?
I just said that because you're getting one from both of those groups of 3, I thought for a second it was going to be like 2/6.
Oh, it's slightly. Oh, call it 2/6.
That's what I thought it was going to be because it looked like 1 out of 3, then 1 out of 3. Putting them together would have been 2 1/6 because it just seemed like that for a moment because the way it was written. But I realize it's not that. I just, that's what it looked like for a second.
Yeah, so it's definitely not going to come out to 2/6, but I can see the confusion on that one right there. All right, let's try this again. What if I tried to show 1/3 groups of 1/2? Can we pull that off? So I want to show 1/3 of something. What am I trying to show a third of? So first I should draw a half, right? This seems, it's kind of backwards in the way I read it. I need 1/3 of something. What is it? It's a half. Okay, let's first establish what a half is. Okay. Right there. So there's my half. Now what do I do? Cut that into thirds. And so I might do the cut the other way method like we were doing before. So I come through and I go, okay, here's it, thirds. So I want 1/3 groups of a half. So that means I just want that one right there.
Which would then be
That's 1/3 of the group of a half, which is really called a,
1/6.
that is 1/6 of the whole, given that a cake is a whole. Okay. Does that match what you used to know about multiplying fractions? Okay. So what we want to do is we want to use these toys, kind of engage kids to play with us, and then eventually after doing a bunch of them, can we come up with a rule? Because I don't want to draw that picture for like 3/30 seconds times 1/11. I don't want to draw that. And most kids I know could not draw that. Okay. So we need an algorithm to jump out of this. Okay. So let's do a different one. Let's erase this crazy one. I'm not ready for that. How about, let's go with 2/3 times 1/4. Okay, so the physical interpretation of that is 2/3 groups of 1/4. Right? Okay, so what do I have to draw first? I have to draw the fourth because I need to take 2/3 of something, but I need to draw that thing first. So I have to draw my fourth. Okay, so I start with my whole, and I cut that sucker in fourths, and then I pick one of them. Like maybe this one right there. So there's my 1/4. What shall I do for the 2/3 part? Cut it, not in half, but cut it in thirds. Yeah, cut it in thirds. So let's see. That's my best attempt at thirds today. And I want 2 of these thirds. So that leaves those 2. Those 2 chunks are what part of the whole? They are, there's 12 because it's 4 by 3. Now, was that a common way to leave the answer? So you guys are dying to reduce it. And reducing fractions happened before we did addition, subtraction, multiplication. Multiplication and division in the curriculum. So a lot of students would say, oh yeah, both of these are even, they both divide by 2. That is 1/6. So now I want to try and justify the 1/6 here. Well, if I divide it by 2, what does division mean? No, division. What does division mean? Like multiplication means groups of, division means combining them. Yeah, groups in, right? So if I divide it by 2, that means I must be able to find groups of 2 in here with no remainder. Right? So I'm just going to double check that. I'm going to use a different color. Let's highlight with yellow. Well, I've already circled one group of 2, right? Here's another group of 2. Here's another group of 2. There's another group of 2. There's another one, and there's another one. How many groups of 2 are there?
6.
And how many am I interested in?
1.
Yeah, so there's my 1/6. Yeah, so anytime you have a picture of a fraction that can be reduced, the number you divided out lives in groups in there. And you can always find them if you're careful. So there's my 1/6. So that's kind of fun. So now after we do a few with the kids, then we start saying, well, do you see a way to get from these numbers to these numbers? And some kids will start seeing patterns, like what could I do to these numbers to end up with those numbers without drawing a picture? I could do what, Minerva? Do some multiplying, like what gets multiplied to get this 2 here? Yeah, this 2 times that 1, oh yeah, that's 2, right? Some kids will see it, some kids won't. How do I get the 3 to 4 to the 12? Yeah, and the kids that are better at the multiplication tables, like they'll probably pick it up quicker. Oh yeah, 3 times 4, that's 12. Oh, there's the answer. This is way easier than addition. They're like, oh, thank goodness. Addition is so painful. And so now we're developing an algorithm. I don't have to draw the picture. I just multiply the numerators, new numerator. Multiply the denominators, new denominator. Right? So the model leads to the algorithm. That's pretty key.
So 2/3 times 1/4. That's what you're saying.
Yes. So we know we were trying to multiply. We know multiplication means groups up. Now, when I was a kid, I was told multiply the numerators and multiply the denominators. Well, why? Why don't I have to find a common denominator? Teacher never told me that.
I was gonna say.
I don't
They never
know.
told
Well, because this is what multiplication means, and a fraction is part of a whole. That's why. The algorithm is a natural consequence of the model. The algorithm is physical reality. The model is physical reality. It leads to a process. We don't have to find did we ever find a common denominator here?
No.
Never did. We didn't have to. With addition, we had to, because we had to count up like things. Like, that's what the denominator is. It's the description. We had to have a like description before we can have it. Here, who cares what the description is? What's that?
This makes that homework part I was stuck on so much easier.
Okay, good. So again, we're coming in with an algorithm now. 2 times 1 is 2. 3 times 4 is 12. Boom, there's an answer. Okay, sometimes I have to reduce. Big deal. Talk more about reducing later. All right, let's jump to division. All right, so models for division. I just mentioned one of them. It was the groups in model. Can you think of any other division models we went over last term? Last year? Oh, that was last year too. Wow. Anyone still struggling with the fact that it's 2016?
Yeah, when I write papers.
Quite used to it. Okay, what else besides groups in did we have for model? What do I multiply by? Yeah. That was also called the missing factor model.
Set partition.
Set partition was another one.
Repeated subtraction.
Yeah, catch up here. This is also called the missing factor. Repeated subtraction and set partition. Is there an E in there?
Yeah, REPEA.
Subtraction. Set partition. That was all. I think we had 4. I'm going to go for the groups in one. Once you move to a new number set beyond the whole numbers, not all of the models make sense when you move on. Some work better than others. Could some of these work to show what fraction, multiplication, or division are? Yeah, they could. I'm going with what I think is the easiest way to model it. So I'm going to try the groups in. So reminder of how groups in works. If somebody gives me something like 12 divided by 3, the question that leads me to is how many groups of 3 are in 12? So then I have to show 12 things. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then I start searching in there for groups of 3. So here's a group of 3. Here's a group of 3. Here's a group of 3. There's a group of 3. Oh, there are 4 groups of 3 there. So the answer must be 4. So we're going to try a similar thing with fractions. And I'm going to use some toys. Oh, I forgot my toy box. Get my toy box. So I'm going to grab my online toy box. Let's use the pattern blocks. Okay, can you see my pattern block screen, Debbie?
Yes, I can.
Pretty soon it should pop up with pattern stuff. It's loading, loading, loading. Okay, so I'm gonna, I gotta blow it up first. That big enough? I think so. I try to go one bigger, that's not bad. All right, so there, we were using that as a whole before, and then this green thing was a 1/6, and the red thing was a 1/2. Okay. So I'm going to start off with an easy problem based on these guys right here. So just get a screenshot of that. All right, so earlier in one of our activities, at least one part of it, we said this sucker right there was 1 whole. That made this guy 1/2 and this guy 1/6. So I'm going to try and do the division problem. 1/2 divided by 1/6. So the interpretation of this is how many groups of 1/6 are in 1/2 is the question. And we can just kind of look at that and say, oh, I can put 3 of those in there. So the answer must be 3. Not too bad, is it? Let's do a slightly harder one. New picture. Let's bring in that guy right there. Page, screenshots. How about, let's see, what would the blue one be? If this is a whole, that would be 1/3, and this guy right here, that's still my 1/2, and this one's my 1/6. So let's take 1/2 divided by 1/3. So write down what you think the question is being asked here, based on the groups in model. Write down the question. How many groups of 1/3 are in 1/2? Okay, so let's see. So let's go back to my toy screen. So I kind of picked this guy up and I set it down there. For sure there's 1 group in there, but there's more than 1. How much more? There's 1.5 groups of the blue thing and the red thing? Does that seem reasonable? Right, because that isn't that triangle, that missing chunk there. Oops, I need a new triangle. And the triangle is half of the blue thing. Yeah, so it looks like, according to that, go. Oh shit. Oh, stop. There it is. Okay. There are 1 and 1/2. here's a slightly different way of thinking about it. Didn't I have to use the green shape to kind of sort that out? Because there was a leftover triangle when I put the blue thing on the red thing. Well, I could just think about it in terms of triangles. How many triangles live in the blue thing? 2. Okay. So I want those. Okay. So I'm looking for groups of 2. Agreed? 2 triangles. I have what? A group of 3. So I'm looking for groups of 2. I have a group of 3. And so it's always the answer. Oops, wrong color. Let's make it so we can see it. It's always what you have divided by what you need. I have a group of 3. I need 2. Is there a relationship between 3/2 and 1/2?
That's the same thing.
Yeah, same thing. Improper fraction versus the relationship. Does it make sense the way I'm thinking about it? Right? I'm looking for rhombuses inside the trapezoid. Well, I could consider the rhombus as 2 triangles, and I could consider the trapezoid as 3 triangles. So I'm looking for groups of 2. So I could restate this. How many groups of 2 are in a group of 3, given those toys? So the answer must be 3 out of 2. I have 3 out of 2, which turns out to be 1/2. That's not bad, is it?
Now the algorithm makes sense.
Yeah, so then the question is here, why do we multiply by the reciprocal?
Yeah.
Well, the more you model it, you see, well, there's no choice because of what you're looking for and what you're looking in. The 2 and the 3 got flipped, right? The 3 is now on the top when I look at it that way. Okay, so again, there are some other algorithms for multiplication and division, but I'm not going to cover them. We're going to kind of stop it there. We have different ways to model multiplication and division. It turns out the easiest way to model division back here is with the groups in multiply, back from whole numbers. Next class, we'll give some of these other ones a shot, like the repeated subtraction and the missing factor one. I'm trying to remember if I've ever tried to use set partition. I guess I'll try it, but I'm not sure if I'm willing to do it on live YouTube. As far as the multiplication went, we ended up using the groups of as the easier model to work with. It's possible to make those other ones work too. Like the area model. I'll point that out before I shut up here. Let's see. This next one. Yeah. Does anyone see the area model living in this picture I drew for the groups of? Yeah. I started with an area of 1 whole, and then I cut it in halves and thirds, and their intersection is where my answer came from. So this little region right here, isn't it 1/6 of the whole area? Yeah, so it turns out if you draw cakes, the area model and groups of are the same thing. Turns out they're the same thing. Doesn't always work that way. Does here. All right, we need to take a look at our projects next. How are we doing on time? Beautiful. So if you have your activity workbook with you, get it out. The next 2 projects we need to do are 8 and 9. Let's see, documents. Alphabetical order. And chapter 6. And 7, 8. Okay. So the multiplying fractions, this is the groups of model going on here. So let me just demonstrate to make sure it seems consistent with what I was doing a minute ago. Let's blow this up for our Audience online. Too big. All right. So here we're using a hole as 2 hexagons. So we're going to stick with the pattern blocks here. We can do this with paper folding also, and that'll come up at the end of this activity. So here we're asked to find 2/3 groups of 1/4. 1/4. And we learned earlier that we have to draw the 4th first. Once we draw the 4th, then we can cut into thirds and then choose 2 of them. And so then in 2 stages, we end up drawing pictures that isolate our answer. Okay. Can you see how that's happening here? I take my 1/4 of the whole, then I try to find 2/3 of whatever I have there. And now I have to decide that dotted region is what part of the whole thing. Well, there's 2 pieces in there, there's 12 in the whole, so I could say it's 2/12. With me? And then we could reduce that. Other ways to reduce it are, what shape does my answer form there? A rhombus, doesn't it? My answer's right here. Yeah, so then I could try and tile the rhombuses through here and see that 6 of them fill up the whole thing. But didn't we decide back here, and actually the book helped us, get there, get there, get there, get there, get there, right here, that the rhombus is 1/6 of the whole thing, right? So if I remember that from the previous playing around with these blocks, some kids would look at it and go, oh yeah, that's 1/6 of the whole, the answer's 6. Other kids will look at it and they'll see 2 out of 12 triangles, right? Different brains work different ways. Let's get back down to that. So let's try another one together. Here's another thing. How many people are good at drawing hexagons like this? Just me and Christian. And some days I'm not good at it. So on the website, I put something that will help do this. Let's switch to the course website. Under online graph paper, one of my favorite websites to go to is incompetech.org or com. I always thought it was a weird name, Incompetech. Sounds like incompetence. But they have great stuff on their website. And they have a hexagonal paper. Error. Error. Okay, let's try another one. Isometric. Error. Well, crap. Okay, let's go to Incompetech directly. Let's just search for graph paper. Graph paper. And one of the first hits on graph paper is going to be Incompetech. And then they have all kinds of graph paper there. So I'm going to come down here, triangular, hexagonal, that section. And so the isometric dot paper is a nice one. Let's make the dots black, download PDF. So this is what was supposed to appear when I hit that link. If there's something wrong with our course website. All right. It worked on yours? Okay, so I don't know what's wrong with my connection. That's kind of hard to see, so let me drag that in here.
Those are under triangle hexagonal.
Okay. Yes. So let me see, I need to see my tools. So copy that in. Screen capture. All right, so let's grab a chunk of that. Roll it up a little bit. So then what I can do is I can use these dots to draw my hexagon. So if I just go bing, 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 and I can draw another one next to it. And so they're just designed to make drawing those just a lot easier. Ooh, I drew them the wrong way. I guess I should have drawn them stacked, so that they were connected like the picture in that activity. Stop. Okay, so I'm going to drop the next one to show you what your work should look like for this. So I'll print out a bunch of this for y'all, and Debbie, you can find that, hopefully alerts for you on the website.
Okay.
So let's take 3/4 times 1/3. Let's do number 2. So 3/4 times, what was it?
1/3.
1/3. All right, so that means I want to find 3/4 groups of 1/3. So that means, again, groups of. So first I have to establish what a 1/3 is here. And well, a rhombus is a sixth, and so 2 of them would make a third. So if I take a rhombus like this one right there, and I combine it with that guy right there, that whole region is then a third of the whole. Right. And just to double check that that's the case, I'm going to just draw in some other rhombuses by doing, let's see, oh, am I doing that right? Oh shit, I do that one. That line goes there. I take that middle line out. Can you see the 3 of those shapes right there? I think, what's that shape called? A chevron, maybe? Yeah. So there's 3 chevrons that live in here. So there's 1/3. So now I want to take that 1/3 piece shaded there and see if I can identify 3/4. Well, what shape comes to mind to do that? Green triangle. Okay. So if I think green triangle, oops, switch to green. Hey, check it out. I've got 4 of them in there. I need 3. So this section right here is definitely my 3/4 of 1/3. Well, looking at that, I have 3 chunks out of, how many chunks would be in the whole piece? 12. Does anybody see another way to look at it? So this is my answer right here. What's another way I could look at this to get the answer?
3 times 1, 4 times 3.
Well, I don't want to get to the algorithm yet. Just look at the shapes. Is there a way to use the shapes to come up with another way to state the answer?
What if we take the rhombus?
Yeah, this guy right here is a trapezoid. Yeah. So how many trapezoids live in the whole thing? Yeah, there's 4 of them, and from our key earlier, oh yeah, right, the trapezoid was 1/4 of the whole. So can't we justify 1/4 as an answer here? Right, without even actually talking about reducing or doing any multiplication. Notice I've avoided cross-canceling. I'm doing that on purpose. I'll talk about that next week. So we can also justify that 1/4 is the answer, because I have 1 out of 4 pieces in the whole. I should draw them just to be clear. There's another 4th. Here's another 4th. And here's the 4/4. So that justifies my 1/4. Okay. All right, so your job is to try and illustrate the multiplication. Sometimes you can do it in one picture, sometimes it takes a couple of pictures to do it, like they do in their illustration at the top. I bet that after you do a couple, you'll probably be able to illustrate it with more. Now I'm using color. The author of the workbook here used different kinds of shading to make it happen. So you'll keep that in mind as you're doing yours. You might want to use different kinds of shading. Let's take a look at the next activity, number 9. Oh, the challenge on this one, they bump it up to 4 for a whole, 4 hexagons for a whole. Like when we were doing addition, we started with 1, we jumped to 2. So that makes it a little more challenging, but it's the same process. You will struggle with those a little bit to draw them right, and the hexagonal paper will help. And then paper folding is at the end. Okay, coming down to division. Now here, it's kind of cute. They use the division, the long division box to kind of show this in terms of looking for one set of groups and the other. But they're using the groups in model. Okay. How many groups of 1/2 are in one whole? And same thing we were just talking about. And they're illustrating slightly different. Some things I didn't mention earlier about division. The fraction bar means divide, right? That's one of our models for fractions. We have this division symbol on the screen here, the line with 2 dots. And then, don't we have another division symbol? The slash, yeah. And usually when I'm working with kids in division, I kind of separate, oops, 10, for division symbols. We have the fraction bar, things like that. We have this division symbol here for 12 divided by 3, and we have the slash. Notice the order of the numbers, like top to bottom, left to right, kind of matches with all of those. But then all of a sudden we throw this other long division box in, and we're going to write 3 goes into 12. The order changes. What should the 1/3 turn into? How many people want to say 1 goes into 3? That's a common mistake, right? I make it, and kids will make it left and right. And so usually I say this is a different symbol. This is the goes into symbol. Because it does behave different, and it does order the numbers differently. And so there's a big difference between these 3 symbols and this one right here. And so we should be careful with kids to treat them different. They all mean division. However, this one behaves very different than the other ones do. The order being different. So a little caution with that. So let's try one of these division problems from the worksheets. How about number 2, 1/2 divided by 1/4. Oh, that one's pretty straightforward. 5, 6 divided by 5. Let's do number 4. 3. Oh, we have another one? More on the next page? Oh, then they make it a little harder here. So let's go. Let's do number 4. 3/4 divided by 1/4. So jumping here, I want the dot paper. Copy part of that. Make it slightly bigger. So let's see. What was a whole again here? Is it 2 things are a whole? Okay. So if 2 things are a whole, then a quarter would be a rhombus. No, a trapezoid. So here's my 1/4. And I want to take that quarter, color, into 3/4. And so then I'm going to have to draw a whole. And so here's what this dot paper is really going to save on butts, making our pictures easier to draw. And so let's see, 1, 2, 3. So here's my 3/4. So how many groups of 1/4 are in 3/4? 3. You get that answer pretty straightforward there. Not too bad. So I don't think you should find this one too much trouble after we've played around a little bit already. Let's see if there's any more interesting ones on that page we could tackle together before we part ways. This class is almost over. Let's see, on the next page, they're saying 1/2. Okay, so 1/2 divided by 1/3. This is a cute one to do. We did this problem earlier with different shapes. So we're going to try this one right here. So 1/2 divided by 1/3. Let's try that. Page. So 1/2 divided by 1/3. So the question is here is how many 1/3s are in 1/2? So So let's see, what's a third look like here? It's that chevron looking piece, right? I'm going to try and draw that. Two blue things stuck together. So let's see, here's one blue thing. And then here's another blue thing stuck to it. Okay, so there's my 1/3. And I want to see how many of those live in 1/2. And over 1/2 is not too bad. Half would be 1 hexagon. All right, so when I start messing with that, let's go back to blue. Well, here is one of those, right? But then I have this part right there. How would I describe that part compared to what I'm looking for? I'm looking for this guy here. What's that remaining? I found one of them was the remaining chunk. It's a half of what I'm looking for, isn't it? So doesn't it look like there's 1 and 1/2 of the chevrons inside the hexagon? And that's the answer we came up with before. So let's look at it a slightly different way. If I'm using the hexagon as my piece, how many hexagons, no, what are they called? Rhombuses, sorry. How many rhombuses live in this chevron?
2.
There's 2 of them. And how many of those rhombuses live in my hexagon? There's 3 of them. Okay. So I have 3, and I'm looking for 2. Remember that relationship, have over need? Okay, so there it is again. So it doesn't matter too much what the pieces you use are. We could use rectangles, we can use double hexagons, single hexagons, we can make it work out. Sometimes one shape might be easier to draw than another. All right, let's see, is there anything else I wanted to go over before I set you free? Yeah, so then they ask us to use the pattern blocks to try and solve these problems here. Describe how you could use fraction strips. And then we want to be able to write a rule for division. So give those a shot over the weekend. Give the homework for section, this is section 3. Give the homework for section 3 a shot over the weekend. And then we will tidy up our work in section 3. Let's see. Chapter 6. And then we have one more section to finish up in chapter 6. Fractions. Get done with fractions.
So if we
What's happening?
if we started 6-3 but we don't finish it, are we still getting docked points? Or we okay?
There's no document point. You just have to ask for the password.
Okay.
So, so this means we'll have a test the week after next. We just about done with 6-3. We got a little work to do in 6-4, and then we're going to take our first test the week after next. We have no class Mondays. That means we're going to see you guys. So have a good week. Stop recording. How you doing, Debbie? Do you have any questions?
No, I think I'm good. Thank you.
All right.